Hello everyone, my name is Paweł and today I'm going to present you our paper entitled Data-Driven Scheduling in Serverless Computing to Reduce Response Time. This work was done at Institute of Informatics, University of Warsaw in collaboration with Bartłomiej Przybylski and Krzysztof Rządca. Our motivation came from current trends in cloud computing. Nowadays, Function as a Service is an emerging cloud computing model. Currently, all major cloud providers offer serverless products like Lambda in Amazon Web Services, Google Cloud Functions, or Azure Serverless. In this model, customer specifies a code of a single function instead of providing containers or whole virtual machines. The function code is executed in an isolated execution environment, which provides required runtime appropriate to use toolkit. For example, Node.js with all libraries required to execute defined function. Each function can be invoked by an external event, for example, HTTP request. In our work, we analyze following serverless computation model. The functions are invoked by HTTP requests incoming from the internet. The function execution environments are running on computing nodes, which are shown on the right side. In presented example, we have 12 individual function calls. The requests incoming from the internet are distributed to working nodes by a load balancer. Each function may have parallel invocations. We indicate this fact by setting distance colors for each function. In particular, we indicated colors corresponding to red, green, and yellow function type. While the data center contains thousands of worker nodes, we ask if there is possibility of improving overall performance by performing modification only on node level. Therefore, we will further focus on a single node and ignore all events occurring on other ones. In considered scenario, we assume that all required environments are already deployed on worker node. Therefore, we do not consider cold starts that usually occur during creation of the environment in function as a service systems. Our goal is to minimize performance metrics related to response time. These metrics in a natural way reflect end-user experience, and we will describe them later. We make scheduling decisions only by using information that can be gathered locally, like execution times or call frequencies. As we mentioned before, we do not consider events occurring on other nodes. We also do not take into consideration decisions taken by load balancer, especially how overall load is distributed across the nodes. Our aim is to show that overall performance can be improved on the node level. In our model, we consider a machine with constant number of processors. In presented example, we have two processors, P1 and P2. One processor can execute at most one invocation at a time. The machine has already deployed environments for assigning function calls. In this example, we have three calls denoted as A, B, and C. Each call is connected with separate function. Here, and on following slides, we distinguish functions by different colors. For each call, we define the moment of call, completion time, and processing time. With these values, we can define basic latency measures, such as flow time as the difference between completion time and the moment of call, and stretch as flow time divided by processing time. Please note that in presented example, calls A and B start just at the moment of their call. Therefore, their processing times are simply difference between completion time and the moments of call. Contrary, task C is called when both processors are occupied. Therefore, its processing starts when one of the processors becomes available. We determine quality of service of schedule with different metrics. First, we consider average flow time and average stretch. Both of them are obtained by computing average over their values for all function calls in analyzed time window. In similar way, we also take into account 99th percentile of both function time and stretch. Furthermore, we consider average function aggregated flow time. In this metric, for each function, we compute average flow time by taking into account all the invocations for this function. Then, we compute average of results obtained for all functions. In similar way, we analyze average function aggregated stretch. For each function, we compute total flow time of all invocations of that function and divide it by their total processing time. Then, we compute average of results obtained for all functions. In our work, we consider two main groups of the algorithms, preemptive and non-preemptive algorithms. We further analyze results obtained in each group separately and show performance benefits for each category. For non-preemptive algorithms, we use classic first in, first out as baseline. For preemptive algorithms, we compare our results to round-robin. We analyze behavior of the following algorithms. The first shown is FIFO, first in, first out for non-preemptive variance. Next, shortest expected processing time, also for non-preemptive case. In this case, when a processor is available, it is assigned the invocation with the shortest expected processing time. Next one is FC hash, that is fair choice based on number of invocations. In this algorithm, when a processor becomes available, it is assigned the invocation which is the most unexpected. In other words, we give higher priority to functions that are called occasionally. Next algorithm is fair choice based on the total processing time, denoted as FCP. In this algorithm, when a processor becomes available, it is assigned the invocation related to the least demanding function in total. That is, the priority of the call is determined by maximum of expected total processing time in considered 1 minute interval for particular function and the actual value of its total processing time. Next we have round-robin, which we treat as a baseline for preemptive case. Finally, we have shortest expected remaining processing time. In this algorithm, when a processor is available, it is assigned the invocation with the shortest expected remaining processing time. We apply this strategy only when an invocation is finished or a new call is received, even if all processors are busy. Such restriction is introduced because otherwise executions of the functions with increasing expected remaining processing times could be preempted an arbitrarily large number of times. We compare different variants of our algorithms. First, in variance using foresight model, we used actual parameters of the distributions used to generate test instance. These parameters correspond to perfect, clairvoyant estimations. On the contrary, in variance using reactionary model, we make estimations basing on all the previous invocations of functions, that is, the calls that have been already scheduled. This situation is more close to real-world scenario. However, in a real system, keeping information about all the previous calls of any function is not practical. Therefore, we introduce limited reactionary variants of these algorithms, in which we keep information about at most 1000 last invocation of each function. We also tested this model limited to 10 and 100 invocations, which resulted in significantly worse performance. Here we present an example of shortest expected processing time in reactionary variant. We have two processors, P1 and P2. The processors just completed executing invocations B and C. We have queue of 4 incoming invocations. The invocations D and E have the same function as A. The invocation F is the same function as C, and invocation G has the same function as B. As functions are invoked repeatedly, we can estimate call frequency and expected processing time of each function using historical data. Here, and on the next slides, our estimations are indicated with dashed border of the boxes. Having estimations of processing time of each call, we can reorder queue by shortest expected processing time. Therefore, in the next step, we schedule calls F and D. Now let's assume that both calls F and D complete at the same moment. Call F took slightly longer than we initially expected, and call D was significantly shorter. We update our expected values. In the result of this process, expected processing time of call E decreased. In this case, the order in queue remains unchanged. However, in general scenario, the scheduling order might be affected every time we update our statistics. Finally, we schedule last two remaining calls, E and G. And in this case, it occurs that both of calls were processing slightly longer than expected. The second group of considered scheduling algorithms contains algorithms allowing preemption. We compare our algorithms with round-robin baseline. Let's take a look at the simplest scenario in this classic variant and compare it with one of our algorithms. Again, we have two processors, P1 and P2. Imagine that initially all processors are available and we have in queue three invocations, A, B, and C. Each one of them is connected with different function. First, call A is scheduled on processor P1 and call B is scheduled on processor P2. Both calls will execute for a fixed amount of time. Then, in the middle of their execution, invocation D arrives and is placed at the end of the queue. After a fixed amount of time, invocations A and B are preempted, and invocations C and D start their execution. Invocations A and B are put back to queue. We assume that both invocations C and D complete at the same time within this fixed time window. After that, invocations A and B continue their execution and both complete. Now let's compare this scenario to shortest expected remaining processing time algorithm. In similar way as in shortest expected processing time algorithm, we can take into account expected processing time in preemptive variant. Again, we have machine with two processors, P1 and P2. Imagine that all processors are available, and in queue we have three calls, A, B, and C. We assume that we already proceed calls of red, green, and yellow functions. Therefore, we have estimations of processing times of all calls in the queue. All calls in the queue were not executed yet. Therefore, we order them by their expected processing time. In present case, calls C and A will be scheduled first. Then, after we start processing calls A and C, at time t1 a new invocation D arrives. Now we compare expected remaining processing time of the calls. As call D has lower expected remaining processing time than call A will be preempted and put back in queue. Then the execution continues to the moment when next of the invocations completes its execution. In this case, call C completes. We again compare expected remaining processing times. As call D has lowest expected remaining processing time, it will not be preempted. As call A has lowest expected remaining processing time among all tasks in queue, it will be scheduled on processor P1. We compare behavior of our algorithms by simulations. We use Microsoft Azure Functions Trace to create test samples. Azure Function Trace provides information about function invocations collected between the 15th of July and 28th of July 2019. The trace presents a number of invocations of each of the monitored functions during each minute within trace period. We generate our test instances using the trace data. First, we specify the number of available processors, desired CPU load, and time duration. For each configuration, we generate 20 independent samples. Our approach gives significantly better results than FIFO and round-robin baselines. Here we show results for the average function aggregated flow time metric. The results are divided into two groups: preemptive algorithms on the left and non-preemptive on the right. The results of preemptive algorithms are normalized to round-robin, and the results of non-preemptive algorithms are normalized to FIFO. In both cases, the baseline is indicated by red dashed line. In presented case, all experiments were evaluated on 20 CPUs with 90% load and 30-minute time frame. Each box corresponds to 20 individual samples. For considered performance metric, our proposed FCP, FC-hash, shortest expected remaining processing time, and shortest expected processing time algorithms improve the results compared to the baselines. For comparison, we also show results for classic shortest processing time and shortest remaining processing time algorithms. Along with different algorithms, we can see different variants denoted by different suffixes. Forced variant denoted by suffix for, reactionary variant denoted by suffix ra, and reactionary limited variant denoted by ra lim suffix. In most cases, this variance provides similar results. We perform comprehensive simulations comparing multiple metrics, different timeframes, various CPU loads, and changes in number of CPUs. Please refer to our paper for more detailed information. To sum up, in the base case of our simulations, our proposed shortest expected processing time and shortest expected remaining processing time strategies reduce the average flow time by a factor of 1.4 in preemptive variant to 6 in non-preemptive variant, comparing to round-robin and FIFO. Our newly introduced fair choice strategies outperform other implementable algorithms when measuring flow time. The performance of the fast cluster can be improved by performing node-level optimizations, and proposed strategies can be implemented with no significant increase in the consumption of memory or computational power. This research is supported by a Polish National Science Center grant Opus. In case of any questions, feel free to contact us. Thank you for your attention.